So we're going to go over the first question that you asked. A website keeps track of predictions made by individuals in finance, politics, sports, and entertainment. The website kept track of 683 stock predictions by a famed TV financial personality and found that 319 were correct predictions. Treat these 683 predictions as a random sample of all of the predictions. Does the sample evidence suggest the TV personality is correct less than half the time? Okay. So what you're kind of happening here is we have this sample proportion of 319 correct predictions out of 683, which is about 47% of the time. So we go through, we take the sample of 683 predictions. We see if the predictions that he said, whether they went up or went down or whatever that he did to predict it, if they were right or not. And we measured if they were right, then he got a message, a count in the right column. If they were wrong, then he got a count in the wrong. And here, our X here is the number of right predictions. Okay, so you go through down here and we look at what is the variable of the variable of interest of study. So is it qualitative with two outcomes? Explain. So remember, we're measuring right here the number of right predictions. That's what we're measuring. That's my variable of interest. I go through, look at the prediction. If it's right, I count it. Okay, so that's going to be my variable of interest, is whether or not the TV personality made a correct stock prediction. Okay, so if I asked you, was it correct? You'd say yes or no. So the answer right there is qualitative. And so it's going to be a qualitative. And there's two outcomes because it's either he was right or he was wrong, right? What's the goal of the research? Okay, so we go through, we get the sample, and the sample has 47% of the time he was correct in his predictions. Okay, so if he was doing this just by chance, he'd have an option to be right or to be wrong. He'd have a 50-50 chance of being right or wrong in his predictions, right? So what I want to know is, it says right here in the problem, it says, does the sample evidence, which is this information, suggest that the TV personality is correct less than half the time? Okay, so that's what I want to go and investigate. Okay, so the goal of the research is to determine whether the TV personality is correct less than half the time. Okay, so I asked for what are the null and the alternative hypotheses. So remember, the null hypothesis is like the status quo, what's accepted already, that it's by chance. These are all these different ways of interpreting this. Okay, so what is the probability that he just chose and made his predictions by chance? Okay, he has two options, and so the prediction would be that, and remember this is a proportion because we want to know if the sample proportion, the population proportion, what is that? What are we assuming to be true? This is what we assume to be true. Okay? If we are assuming that he's doing it by chance, then my proportion is going to be 50% chance because he has two options, he has two choices. He has one option out of those two choices. If by some chance he had three options, like maybe he was right or he was wrong, or like it was a neutral prediction, right? Then maybe he'd have three options and he'd have one out of three. But here we only have two options and we have one out of two chance that we're going to be that scenario. Okay, the alternative hypothesis is what we want to find evidence to support. Okay, so remember up here it says that what was the goal of the research? The goal of the research is to determine whether the T personality is correct less than half the time. So that means that my proportion is going to be less than half the time. And this is the null, and this is the alternative hypothesis, H0 and H1. Okay. So, when you go through, it's to Angela's question, you want to kind of see, okay, well, if I chose 683 samples over and over and over again, what would the proportion of them being correct predictions be, right? And that's hard to do. You can go through and, like, you're not going to ever have those same situations again. So you can't get multiple scenarios because you want to see the sampling prediction, the sampling the sampling distribution, because then we can kind of see where this proportion is, anything less than that, right? So it's hard to do. So instead of doing that, we go through and use flipping coins, because flipping coins has two options and we can count those, right? So we said that we had two options, whether we were right or we were wrong, right? So we had these two options of being right or wrong, and we had one of those. So if I wanted to go through and flip a head, probability of that happening, it's going to be 1 out of 2 because there's two options and I have one choice. It's the same thing. So I can go through and utilize a coin to represent this. I also could utilize like a dice, one die, and be like, all the odds are he predicted correctly and all the evens are he predicted wrong. However I want to do it, I got to find some way that I can do over and over and over really, really quickly so that it is useful to do that instead of going through and actually choosing 683 predictions and looking at the proportion. Okay, so we choose 683 fair coins so that the probability of heads equals probability of tails, which is 0.5. Each coin represents a prediction. For each coin, record whether the TV personality is correct, which is a head, or incorrect, which is a tail. Okay, so it's going to be a simulation. We're going to do that over and over again because we can flip a coin a lot of times, and we have to actually make a prediction and see if we're right or wrong. Okay. Okay. So we're going to use this coin flipping applet in StatCrunch to build a model described in Part D to simulate 2,000 repetitions of the study. So we're going to go through, and instead of actually flipping the coin 683 times, we're going to make the computer do it. Okay? And we're going to make the computer do it and flip 683 coins 2,000 times. And we're going to see how many of those did we have a heads, which is our correct prediction, 319 times or fewer. Okay? So what you go through and do is you go to StatCrunch to get this applet. And once you go to StatCrunch, you see applets and you scroll down to where it says simulation, and then what pops up is these different options, and you're going to go do coin flipping, and you're going to get this output. Okay, you see a similar option as this when you click on in the problem. Up here it says shown here. It'll get a similar scenario, which we'll look at in a minute, as what we're going to go over in a minute. Okay, so we're going to simulate these coin tosses as being right or wrong in our stock predictions. Okay, so the probability of getting a heads is 0.5, right? If you flip a coin, you have 50% chance of getting a heads. And then we're going to do this, flipping of a coin, 683 times, because it's going to simulate the 683 stocks that the T personality used and predicted on. Okay? And what we want to know is if these number of heads is less than or equal to 319. Okay? Because that's what our actual sample information is. Our p hat was 319 out of 683, which is about 47%, remember? So I want to be like, okay, so if I flipped 683 coins, would I very often get fewer than or equal to 319 heads? Okay? You can imagine that happening, and I want to know how likely would this happen, because that's going to help me to know how likely it is that my TV personality is, in actuality, in the population of predictions, predicting right less than half the time. Okay? So again, you go to the StatCrunch, you find the simulation, you find the coin flipping, and you get this dialog box that opens up. Okay? So we go through and we write it at the beginning. Probability of heads is 0.5. The number of coins that we're going to flip is 683. Okay? And you want to know what are we looking for? I want to know how many times would I get fewer than or equal to 319 heads. Okay? By default, it does a dynamic seed here. Since we're doing this on StatCrunch and I want to check if you're doing it right, they are giving you a specific seed, which tells you it's not going to be random so much. It's going to be random for all the students. It's the same thing. If you did a dynamic seed, you get very similar answers. But just like when you flip a coin 683 times, you're not going to get the exact number of heads every single time. But when we do a seed, it tells the random number generator how many heads to get. It's like one situation when they're going through and doing it. So they can judge you on that and they can grade you on it, okay? So that's how you go through when you do your inputs. And then you push the compute button. Okay? So now you get a screen that looks like this. Okay? So we're going through and we want to know, because remember the problem says, simulated with 2,000 trials of flipping 683 coins. So you're going to go through and you're going to push 1,000 runs. So it's going to be flipping 683 times 1,000 times. Okay? And if you have the fixed seed, your output will look like this. Okay? So I went through and I flipped 683 coins 1,000 times, and the number of those 1,000 times that I flipped 683 coins that I got fewer or equal to 319 was 45 times. Okay, and they're highlighted here in red. Okay, and if you go look on the runs, they're going to be highlighted in numbers that are the trials that ended up getting fewer than or equal to 319 heads out of 683 coins that I flipped. Okay, and this proportion is going to be given your p-value, but we don't want 1,000 times, we want 2,000 times, so you got to push 1,000 runs again. And now we have 2,000 trials of flipping 683 coins. And out of that, we had 83 of those trials had fewer than or equal to 319 heads. Okay? Which is, again, this here, highlighted red spot. And if you go through and look at the runs, it'll tell you which runs did that. You might be able to click on it and get more information. And we have this proportion here, which is my p-value. Okay? So this proportion is the p-value. So what does the p-value mean? Okay? So it is remember, empiric probability is actually doing it. It's empirical, but we're doing it through a simulation. Okay? So it's the probability that we would flip 319 or fewer out of 683 flips if flipping a head has probability of 0.5. Okay? So you're like, okay, we would expect about, our p-value up here was 0.0415, rounded, if you wanted to, like ask you to, 0.042. And you're like, okay, well, that means about 4 times out of 100, I would expect to get 319 coins or fewer if I flipped 783 coins. Okay, so it's not very common, right? I mean, it's not impossible. There's a pretty good area here that is highlighted red, and 83 out of my 683 times were fewer than or equal to 319 heads. But it's like, okay, and we're assuming that flipping a coin is a 50% chance of getting a head. Okay, that's what it says. And remember when we did our probabilities, that if we do the empirical rule enough times, the empirical probability enough times, if we did it more and more trials, it would converge to the actual probability. So that's what we're doing. We go through and we did it 1,000 times, and we did it 2,000 times. So we went through and did it a lot. So those probabilities are going to be closer and closer and closer to the actual probability of flipping 319 or fewer coins if I flipped 683 coins, assuming that flipping a head has a probability of 0.5. Okay? So, in other words, it simulates the probability of the TV personality being correct less than 319 or fewer times, assuming that he's guessing, and that there is a 0.5 chance of being correct. Okay? In other words, the p-value is the probability of getting at least as extreme as an outcome as we got, assuming the null hypothesis was true. Okay, so we're like, okay, we got 319 out of 683. That value, or more extreme, which is more or even fewer than that, probability of getting that 319 or fewer, if I flip 683 times, is going to be my p-value, which was about 0.042. Okay, so now we have a p-value. Let's go through and conclude what's going to happen. So we're going to conclude using our significance level alpha of 0.05. Okay, so if the p-value is less than our significance level, then we're going to reject the null hypothesis. So if we go through here, and our p-value was 0.042, and my alpha, which is my significance level that we're doing here, which is given to us, is 0.05, and that number is less. So if our p-value is less than our significance level, then we are going to reject the null hypothesis. This means that we have sufficient evidence to believe that the alternative hypothesis was true. So up before, we believed, so the alternative hypothesis way at the very, very, very beginning, right here, was we wanted to find out if we had evidence to support that he predicted less than 50%, predicted correctly less than 50% of the time. Okay? So, we have evidence to support that now because our p-value is less than our significance level. Okay? A nice little like mnemonic device that you can say is, if the p-value is low, then the null hypothesis must go. Okay? In other words, and also if the p-value is greater than the significance value right here, then we failed to reject the null hypothesis. This means that we have insufficient evidence to believe the alternative hypothesis is true. So we keep believing the null hypothesis to be true since we don't have any evidence to support otherwise. Okay? We don't have enough evidence if our p-value is greater than our significance level. Okay, so hopefully that will help. Good luck, and